And we'll get this going. All right, grab some questions from the quizzes. One question is just about how science works. How do scientists know that their research hasn't been done before? Basically with a lot of hard work. When you start a PhD program, so to back up, I guess, the scientists that are actually doing all the real research in our university system are actually the graduate students for the most part. So when you first enter a PhD program, you pick an advisor after a couple months. Sometimes they do like rotations, kind of like in med school. And then you pick an advisor that has like an interest area or has resources that are similar to what you want to study. And then what you do is you basically spend 3 to 6 months doing nothing but reading papers 60 hours a week. It's called a literature search. You do a deep dive into what the current state of science is in the area you want to specifically look at. And it's incredibly detailed down to, very, very small areas. So basically your job for those first 3 to 6 months is to make sure that you have a good idea for a research project and that it hasn't been done in the research before. If you don't do that very carefully, somebody is going to notice like, hey, I saw this paper last year that did the same thing. Have you seen this before? And ideally, you find all those papers yourself, because the next step in getting your PhD is you have to write a project proposal that you give to a group of full professors that are in relevant research areas to what you want to study. And if any of them have heard of papers that you haven't read, you don't pass. So you have to go in there knowing more about it than any of your advisors, than any of your committee members. And then you get to start doing the research. And after you spend a couple, 3 years, 4 years, 5 years, depending on what you're doing that research at 60, 80 hours a week. Then you come back to that same committee and say, here's what I actually did. Here's the papers I got published, things like that. But it's entirely possible you get to about 6 months from that final defense of your thesis and realize somebody did exactly what you did 10 years ago in a different continent. That's the worst case scenario, because then you're basically back to the drawing board and you're probably staying there for an extra 2 years after that. And you're going to be studying something that's not necessarily as relevant to what you wanted to be studying in the first place. So it basically, with a lot of hard work. And if you're looking at like national labs and things like that, all of those scientists have gone through that PhD process already, so they know that and they're already current in their area. And part of your job as a scientist is to stay current with what's currently going on. So it's an ongoing thing, and you hear horror stories from grad students who got all the way up to a week before their defense, and then somebody forwarded them a paper that they'd never seen before. That was exactly what they were doing, and that's a nightmare. Anybody heard of sundogs and moondogs before? The moondog stars at Sushi Pier. They're crab rangoons, are pretty tasty. Basically, they're like they kind of look like little points that happen kind of around the sun when the sun is either setting or rising, or around the moon. It's not necessarily like the full witch's circle around the moon, but basically it's ice crystals in the air. When it gets really, really cold and you get ice crystals in the air, the sun, when the sun is rising, refracts through those crystals, and you get sort of a lensing effect that causes almost like the start of a rainbow. You don't get the whole rainbow usually, because usually those ice crystals are pretty close to the ground when the conditions are right for this. But it's really pretty similar to seeing a rainbow. It's just you're looking through ice crystals, not water droplets. And you don't get that full rainbow. If you have no idea what sundogs or moondogs are, try Googling it. There's some good pictures out there. You can capture it in a picture pretty well. And you can get an idea what we're talking about. It happens a lot in the Midwest in the winter. It happens around here sometimes. We don't really have like long extended flat areas, and it doesn't get cold enough for us to see it that often around here. You'll probably be more likely to see it in Nevada in the dead of winter than you would actually in Tahoe or in the mountains, just because you need long flat area for it to happen, really, for it to be noticeable. Somebody asked about the numbers for Voyager 1 and densities and things like that. I'm always going to try and give you real numbers as close as I can. If I'm giving you a made up word problem that I'm asking you to solve, I'm at least gonna try and make it relevant for the most part and try to include, look up real numbers. So generally speaking, I try to report the numbers and accurate within sig figs too. I don't try to over represent unless I'm trying to make a point about sig figs and I want you paying attention to sig figs. I'll give you realistic sig figs and uncertainty on those as well for the most part. I think because of the rounding on the Voyager 1 question, I think the actual number, if you look at Wikipedia and total distance traveled by Voyager 1, it was actually moving faster than it is currently for a while. And so I think it's actually a little, our number is a little bit low. I think we calculated 173 AU. I think it's more like 175, but pretty close within that margin of error for the sig figs. And basically because the way that orbital dynamics works, things go faster when they get closer to large objects. And because Voyager did a gravity assist around Jupiter and around Saturn, it was moving really, really fast when it did those steps. So it was moving pretty fast for a couple of years before it got slingshot out of the solar system. Multiple questions about if you can't come to your normal lab, really try to come to your scheduled lab section as much as possible because we don't have much wiggle room. We can't go above 24 students in lab if we're doing anything with chemicals for liability reasons. That lab's capacity is capped at 24 for safety reasons. And we have currently on the Monday and Wednesday lab sections, we have 23 students in one of them and 24 in the other. So there's really not much wiggle room there. And that's why and we do have the Thursday lab section, which only has 2 students in it currently. There's always room to come to Thursday, unless there's a big rush and everybody wants to switch to Thursday. That's it, those 2 students, if it's not a computational lab, or if it's not a wet chemistry lab, I'll usually see if you want to come to Wednesday, because if on the days where we're just doing computer-based labs or paper-based labs, then the capacity doesn't matter quite so much. So keep an eye out. That's kind of on a week by week basis, but yeah, there's not much room. You can ask me on any given week if I've heard that somebody else is not going to be there on those full lab sections, and there might be a room. But it's not a guarantee. So try as much as you can to plan to come to your scheduled lab section. Exception being if anybody wants to move to Thursday's lab. Thursday's labs in general are going to be much faster because you're going to get a lot more one-on-one attention and help. And I've already done the lab twice that week, so I remember what all the hiccups are and all that. So there's a lot of advantages to go on Thursday if you can make it work. If not, stay where you are. Just come to your scheduled labs. Last question. You always have to change nano to a positive. Why do I always do that? So if you look at that at our conversion sheet, the box for nano, for instance, says, fight me on this, huh? Says nano, and then it says n, and then it says 10 to the minus 9. What that multiplier is, just to recap, because I know we're all still getting used to this, is that saying if you take the normal unit and you multiply by 10 to the minus 9, you get the nano version of that unit. So you can say 1 nanometer is equal to 10 to the minus 9 meters. Right? And however, you could also go the other way. Instead of saying a really, really tiny fraction of a meter equals 1 nanometer, you can also say a whole bunch of nanometers equals 1 meter. If you do that, that's what that question was asking about switching that negative to a positive. If you want to switch this to it being a positive, you just have to switch it to the other side. So it'd be 10 to the positive 9 nanometers equals 1 meter. So, and again, I've said this before, but I think better in positive exponents. I think most people do. And so the trick with knowing that you have to do it this way is when you see this 10 to the minus 9, you have to know, oh, that means that my unit got smaller. Means a nanometer is smaller than a meter. So in other words, it takes a whole bunch of nanometers to equal 1 meter. So as long as you know it's making things bigger or making things smaller, then you don't need to worry too much about positive versus negative. You just have to think about it logically, right? But both of these will give you the same answer when you plug them into a conversion. This is just the way my brain works, is thinking about it more like this. If this makes more sense to you, do it like that. You don't have to switch it one way or the other. Any more questions on quiz stuff from this week? I also got lots of questions about, are we going to do anything besides conversions in this class? Yes, in fact, today is going to be almost entirely conceptual. Very little math today. However, and that's not because the math's not there, it's because you all haven't taken enough math classes for the math to make sense yet, because we're going to get into quantum mechanics today. Which means talking about waves and wave functions and probabilities and things like that. And it's not something that even the Gen Chem classes doesn't really touch the surface of the math here. When you take the calc-based physics class here, you'll get into the simplest version of a quantum system, which is called a particle in a box. And that's basically pretending you have one electron in a box. How does it behave? Can you calculate how it moves? You get to any system more complicated than that, you can't calculate it by hand anyway. So for the most part, there will definitely be things that are not conversions. We're just always going to keep coming back to conversions because that's going to be our #1 problem solving technique for this class, or the word problems in this class. So I know I harp on it a lot. We're going to do a lot of practice with it, but it's for your own good. Everybody loves hearing that, right? You might not like it, but it's for your own good. Last but not least, next Wednesday, a week from today, closed book quiz on the names of the elements and their symbols. So to reiterate, I'm not going to give you a blank periodic table and make you fill it out. There's no numbers involved whatsoever. It doesn't matter if you know that carbon is atomic number 6. All that matters for this quiz is, you know, if I write C, you write carbon. If I write chlorine, you write Cl. Right? That's the way that the quiz is structured. That just so you know exactly what it's going to look like, so there's no surprises. Let me pull up last year's quiz. Eventually, this will ever catch up. It's going to be 20 of them where I give you the name, you write the symbol, because that's faster usually, and then 10 where I give you the symbol, you give me the name. Right, so something like this. I write neon, you write Ne. And then down at the bottom, there's 10 going the other way. Right, I'm not going to be picky on spelling, as long as a reasonable person could read what you wrote and get to something close. Right? So there's a little bit of a judgment scale in there. Basically comes down to, if you leave out an entire syllable, I'm probably going to mark you down for your spelling. And if it's a really critical letter, like if you're trying to write zinc, and you write it, spell it Linc, that's not zinc, right? You just wrote link. That's a totally different word, right? So that's kind of where I draw the line when it comes to spelling. So beyond that, I don't worry too much about spelling. Which brings us back here. How do you actually memorize all of these? Well, a lot of them are really, really close. If anybody's taken a class in a foreign language, they have those words called cognates, right? The cognate just means it's close to the original or to the same word as in a different language. I'm totally blanking on Spanish. Yeah, no, in Spanish is a good one. Something that's really similar, so like zinc being Zn. That doesn't take a whole lot of memorizing to get that one, right? The tricky ones are the ones where the symbol doesn't match the name. And for the most part, those are gonna be the ones that are gonna be the hardest, but most of them are pretty close to their actual name. So one of the things that I like, and maybe this is just me, liking to geek out about things, but if you find one that's totally doesn't match up at all, like silver being Ag. Well, Ag doesn't seem a lot like silver unless you go look up why it's Ag, and you find out that Ag it actually comes from the Latin, argentum, which is actually pretty close. I think for the Portuguese word for silver is something really close to argentum as well. There's a river in Brazil, in southern Brazil, that's like Rio Argentum or something like that. Maybe I'm thinking of Rio de la Plata. Anyway, there are some, once you know, oh, argentum, that actually kind of helps it once you go out and learn that fact, that kind of helps cement it in your brain a little bit more. And that also does things like making mercury make more sense. Mercury is Hg. Mercury is Hg because it's also from the Latin. The Latin word for mercury is hydroargentum, or literally liquid silver, which makes sense because mercury is a liquid at room temperature, but it's metallic. The old English name for mercury was quicksilver, but the Latin name was hydroargentum. So mercury being Hg actually does kind of make sense. When you know some of those facts, if you go to the trouble of looking up some of those things, you kind of see some of the stories. Makes it a little bit more interesting, at least for me. That always helped me, was learning why they had these weird things. Here's one for you to go look up. I still don't know why antimony is Sb. That's the one I don't know off the top of my head. Antimony, the symbol is Sb. I have no clue why. And that's pretty much the only one I think that I don't know off the top of my head. Most of those stories I've heard over the years, they tend to stick with me. All right, any other questions about this quiz coming up? This will be the one time I tell you to put away your periodic table. You're not allowed to have a periodic table out. After this next quiz, a week from today, there is no point in this class where you have to put away a periodic table. Well, I might give you a fresh one if you've been taking notes on the one that you've had all year. But for the most part, you're going to be able to use a periodic table on everything moving forward, just like the conversion sheet. Second question, not scientists aren't in superhumans. We know the parts of the periodic table we have to use on a regular basis, but it's not like every scientist or every chemist has gone out of their way to memorize the entire periodic table. I still have to search on the periodic table for things sometimes. I still forget where things are. I have the ones that I use all the time, and their numbers and masses for the most part close to memorized, but it's definitely not something that most scientists have the entire thing memorized. Why bother? Einstein famously said, when he came to the US for the first time at one point, I think it was Columbia, one of the Ivy Leagues back east gave him like an IQ test or something like that. He failed it because he didn't know the speed of sound off the top of his head. And so he said, why would I bother memorizing something I can look up in a book? And that was true 100 years ago. It's even more true today because everybody has a supercomputer sitting in your pocket at all times. So you can always look stuff up. I don't care that much about memorizing things, but you've got to get fluent with these because we're going to go back and forth between symbols and names a lot in this class. So if you don't have it memorized, you're going to find yourself getting lost and forgetting why I'm doing what I'm doing for some of these. Right? Beyond that, though, don't memorize things if you don't have to. All right. Let's recap where we were the other day. We ended talking about the difference between elements, ions, and isotopes in our three fundamental, I can't call them fundamental particles because the theoretical physicists get mad at me. The three subatomic particles we'll be focusing on in this class. Turns out they're not strictly speaking fundamental particles because they can get even smaller, but we're not going to get into things smaller than protons and electrons in this class. So when you change the number of protons in a nucleus, you change what element you're talking about. And so for the most part, that's not going to happen in this class. Until we get to talking about nuclear reactions, the nucleus doesn't change. The nucleus is going to remain constant. If you're going to change anything, you're typically going to change the number of electrons. Because remember that our nucleus, where all of our positive charges are, is basically this tiny little blob. And I say tiny, and it's even smaller than you're thinking it is. Because the electrons that surround it, and we're going to talk about electrons, that's the bulk of what we're going to talk about today is electrons, because turns out 90% of chemistry is just moving electrons around. This nucleus, when I say it's small, has anybody been to a professional baseball game, a Major League Baseball game? Has anybody seen a baseball stadium before? If you picture going to Oracle Park in San Francisco, standing on the pitching mound holding a baseball. If that baseball is the size of the nucleus, the rest of the stadium is the size of the electrons. So all of the mass is right here in the nucleus. All of the volume is the electrons, and that's that huge cloud of electrons that surrounds the nucleus. So when we change something about an atom, almost always we're changing the charge because we can take electrons away or put electrons in relatively easy compared to changing something about the nucleus, which is even smaller. And then the last thing we can change are these neutrons, these particles in the nucleus that don't have a charge to them. Right? They have mass, but they don't have a charge. So another way of looking at this slide is we can say that protons have a mass of 1 and they have a charge of +1. Electrons effectively have a mass of 0 and a charge of -1. And neutrons have a mass of 1 and a charge of 0. Right, so when we change the number of neutrons in the nucleus, we're not really changing much. The charges, for the most part, we're going to determine all of your properties besides the mass. How things react, what it's attracted to, what it is repelled by, that's all governed by charge in protons and electrons. The only thing neutrons affect is the mass. Until we get to nuclear chemistry. All right. So let's do some practice. If I give you an element, and remember the number up and to the left means that's the mass number for that specific atom or that specific isotope. So carbon with a mass number of 14. And I realized I did not print out periodic tables. So if anybody has periodic tables out, share with the people around you. I'm going to give you all a few minutes to fill this out while I go frantically print a whole bunch of periodic tables, and I'll be back with periodic tables for y'all.
Those were actual things. Guys, someone to lock it on. Here. They push you up there. I can see it is. Yeah, but because honestly, I'm overthinking this. Yeah. Like I feel like I'm overthinking. When I said it's left, right? Sorry. It's 36. This is really weird. I hear like
No, the entirety was.
I'm back in.
What's that? Did you never seen them passing?
Yeah, and I know it's not so.
That's
He's so much. What was the flow? Oh, it's 11. Like, it's French. I have those meetings. Birthday. And that's so That's a house.
Yeah.
That's one key over there.
I think it's like somebody. Yeah, no, I don't. So instead of. I don't know.
Right.
Oh, yeah.
So it makes it a lot easier to do this problem when you have the periodic table sitting in front of you, right? Without the periodic table, you really can't do this, right? You need to be able to look at where carbon is, for instance.
Yeah.
At the very least, we can fill in element names for some of them. Good way to do some practice. And really, when we say element name, we usually want to include, if we are specifying a specific isotope, we also write that as part of the name too. So we wouldn't just say, if you just say carbon, it's implied that that's what the natural mixture of isotopes is on Earth. So on the natural distribution of isotopes on Earth for carbon gives carbon a mass of 12.011. This is specifically saying carbon with a mass of 14. So we specify that in the name too. So we say carbon 14. Which means this is zinc 65. All right, so if you're saying the name, this is one of the reasons why we need to be really clear about the difference between the symbols and the names. Because if I say carbon 14, that means I'm talking about a specific isotope of carbon with mass number 14. If I say C14, that's implying that there's some molecule made up of 14 carbons. It's a different thing, right? So we don't say, if we say the name with the isotope number, we would not say that's the same way with the symbol. Right? We wouldn't say ZN65. That's just not the common way of communicating it, and that's just going to confuse people if you try to say it like that. So sulfur 32. Depending on what periodic table you look at, you might notice some difference in spelling. Sulfur there's a few elements that depending on where you are in the world, they're spelled a little bit differently, but nobody's going to get mad at you if you spell sulfur the British way with a PH instead of an F. That's still a really common way of writing it. Fun trivia fact about like weird British spellings of things. A fair number of those, like extra fancy letters that they use in words like favorite and color and sulfur and things like that. It's not because in England they were spelling it the real way. They actually went back and decided that they wanted to separate themselves from American English, and they went back and they changed words to make them more complicated so that they could say, well, that's our British spelling. It's not like that we Americans took the British words and simplified them. It's the opposite. The British took the American words and complicated them. For some of them. Some cases it went the other way. But anybody know what the other common one that sounds really funny if you talk to somebody from the UK or Australia? Aluminum. Aluminium. Which actually does add a whole syllable in there. Aluminium is the British way or the Australian way of saying aluminum. So Na with a plus charge, the mass of 23. So that's going to be sodium 23. We want to specify that it has a charge to it as well. So we actually are going to use that term ion. Again, ion is just anytime you've got something that has a net charge to it where your protons and your electrons don't match up, we call that an ion. So we want to be specific that we're talking not just about sodium 23, we're talking about sodium 23 as an ion. We just stick the word ion onto the end. Then for bromine 37 ion, this is something that we're going to spend more time on when we get a little further in, but nomenclature in chemistry is a whole thing we're gonna have to talk about. Nomenclature just means how do you name things. There's a system for how we name things. And if you have a negative charge, you don't just put the word ion at the end. You actually change the ending of the element as well. So it's bromine when it's neutral. When it has a negative charge, it's bromide. So bromide 37 ion. And if you say bromide, if you say ide, it's implied that it has a negative charge. So you don't really need to say ion. It's a little redundant to say bromide ion, because you could just say bromide. If you say bromide, that means it has a charge. So you don't need to say ion as well. But it's not wrong. It's just kind of redundant a little bit. Yeah.
So the "ide" suffix goes with any negative.
Anything that's a negative. So for instance, so that column on the far right of the periodic table, sorry, second from the far right, the halogens, fluorine, chlorine, bromine, iodine, you see this a lot with those. It's not fluorine in our drinking water, it's fluoride in our drinking water. It's not chlorine in our salt, it's chloride in our salt. But also pretty much anything on the right-hand side of the periodic table will take on a negative charge to become more stable. We'll talk about why that is here in a couple slides. But so you get things like nitrogen with a 3- charge is nitride. Oxygen with a 2- is oxide. Phosphorus with a 3- it's phosphide. And so anytime you see that "ide" suffix at the end, that just means it's got a negative charge.
Is there a way of specifying, or is it common to specify how much it's negative in the name as well?
We're gonna come back to that in a minute, but basically, where it is on the periodic table governs what charges are stable. So nitride is always gonna be a 3-, because of where it is on the periodic table. Its number of protons means that it becomes most stable when it's got a 3- charge. Also, one other point about this, the order of these in the charges doesn't really matter. 3- or -3 mean the same thing. And the reason for that is actually bromide is a really good example. Anybody know what kerning is? It's a computer science term. When your font starts running into the letters next to it, that's called kerning. Because if you look at the word kerning, is that kerning or is it chemming? Is that R and an N or is that an M? Well, depending on the font and how you write it, it's hard to tell, right? You could wind up with some fonts where that R bumps into the N and all of a sudden you can't tell what the letter is supposed to be. Chemistry has the same problem with superscripts and charges, especially when you type out bromide with a -1 charge. Depending on how you type it out, what font you're using, you can wind up with it looking like that, which is confusing. So the way that chemistry solved this was basically saying it doesn't matter what order. You can say Br -1 or you can say Br 1-. Solves the issue usually if you just switch the order of them. So all that to say, I typically write number and then plus or minus, but that's just, I'll switch back and forth because they mean literally the same thing. So don't be thrown when you see that. There's no right way or wrong way to do it. Just pick the way that makes the most sense and makes it clear to somebody reading what you're trying to say. All right, filling out the rest of this. What's carbon's atomic number? 6, which means How many protons?
Yes.
6 protons. If it's neutral, how many electrons? 6 electrons. I didn't put in a column, I must have accidentally deleted the column for neutrons. How many neutrons is this gonna have? Does carbon 14 have? 8. Because 6 protons plus neutrons has to add up to 14. Right, so remember that our electrons have effectively no mass. They're so light, we just ignore them. They're lost in the sig phase. So all we're doing to get to this mass number is adding up protons and neutrons. So I'm going to erase this far right side and I'll write in the number of neutrons here. So 8 neutrons. Our symbol for neutrons is lowercase n with a 0. Reminder, we have to be careful about our cases, right? Capital versus lowercase. Because a lowercase p with a positive charge is a proton. A capital P, whether it's a positive charge or anything else, that's phosphorus. Right, so capital letters mean element, lowercase letters mean our subatomic particles. Zinc 65. Zinc is what, 30? Which means 30 protons. If it's neutral, that also means 30 electrons. The total mass is 65, 30 of which are protons, so it's got to have 35 neutrons. Questions so far? Looking good? This is, I'm trying to think of the way that best to set that up. Final for this. This is at least 5% of your final exam. And you count protons, neutrons, and electrons. And it might even be 10% of your final exam. Right here. And it's not hard, it's not tricky math, right? This is not using conversions to solve word problems. This is just literally you look at the periodic table and you just have to know how to read it. Let's skip down to one that's a little more interesting. Let's do sodium ion. Atomic number for sodium is 11. So 11 protons. Now we have a net charge though, so our electrons and our protons don't match. We have an extra proton compared to the electrons, right? 10 electrons. And this is one of the reasons why it's worth writing out. To answer this question, if I just said fill this out, you could just write 11. You don't have to write proton with a plus. But that's going to really cement it in your head. Protons have a positive charge. It's going to get tricky when we talk about electrons moving around because electrons having a negative charge means you lose an electron and your charge goes up. And that's something that's counterintuitive because of the way the charges are. This is the best way I've found to sort of drill it into everybody's head that electrons are negative is make you write it out like this. Well, not make you, but encourage you to write it out this way. Because all we have to say 11 positives and 10 negatives adds up to +1. Neutrons. 12. Let's do the last row. Atomic number for bromine is 17. That's the mass, right?
Oh.
37 is the mass for this isotope. The number on the periodic table, its atomic number, I believe, is 17. No, sorry, I'm off by. How did I get the wrong? Oh, that's chlorine is 37. Change that. That's why it's not making sense to me. 35. And then bromine's naturally occurring isotopes are 77 and 79. So the atomic mass comes out to be about 78 on the periodic table, right? Okay. So 77, not 37.
It's calculating 2 neutrons.
Which would be really unstable. That's one of the reasons why we keep track of neutrons, is what neutrons, the reasons neutrons are even in a nucleus is they basically sort of like mediate between all the protons. Because protons are positively charged, right? So how is it that we can get 35 positive charges that close to each other into one tiny nucleus? It's basically that the neutrons sort of balance out those charges. They kind of work as mediators. And you need somewhere between 1 neutron for every proton, or up gets as high as about 1.6 neutrons for every proton when you get into some of the larger elements. And they're there, I would almost say their job, but it's not really like they have a job. They're not putting on their little neutron suit and going to neutron work. But what they do is basically keep it so that that nucleus doesn't fly apart from the force of all those protons pushing each other away. So if you ever did wind up with a situation where you had 35 protons and only 2 neutrons, that nucleus is going to fly apart and you're going to get a massive nuclear explosion. I don't even think we can make something like that that is that far off on its ratio. So 35 protons, total mass of 77. That gives us 42 neutrons. And then electrons. We have an overall -1 charge, which means we gained an extra electron. So a total of 36 electrons. Yeah.
Periodic table that bromine is 79.5 for the mass. Where'd you get some?
So I was going off of my memory. But also because I know that bromine has 2 isotopes that occur in roughly the same ratio. It must be 78 and 80. If it's 79 on the periodic table, I thought it was 77 and 79. Must be 78 and 80 because it averages out to 79. But it doesn't really matter because if I say this is a specific isotope we're talking about, it doesn't need to actually match what's on the periodic table. So you bring up a really good point. This is the #1 place that people miss points on this on the final, is usually because they don't look at the isotope that I give them, they look at the periodic table, which is going to show you the most common isotope. But sometimes we're talking specifically about a different isotope, like carbon-14 is the specific form of carbon that we use to date things that were once living. We can date how old an archaeological find is going back to about 50,000 years by looking at how much carbon-14 is in it. We don't care about carbon-12. Carbon-12 is the most common form of carbon that we find on Earth, but that's not the form we use in carbon dating. So if you just looked at the periodic table, you would say, oh, carbon-12 is the most common because its number is closest to 12. So I'm going to say it's got 6 neutrons. If we're specifying a specific isotope, looking at the periodic table is only going to get you your protons. And you have to do that subtraction to get the rest of it. Right, and if you want to get an idea of just how many different versions of how many different isotopes you can find, what's a good one? Good look at, oh, look at carbon. If you just search up carbon isotopes, one of the first things after the garbage AI overview is isotopes of carbon, Wikipedia page. And it gives you a little overview at the top. Carbon has 14 known isotopes. From carbon 8 all the way to carbon 20. The only ones that are stable, and from a nuclear point of view, are carbon 12 and carbon 13. That's why carbon 12 is what's most common on Earth. But we can make all these other ones in particle accelerators. We can slam stuff together to make carbon 9. Carbon 9 has a nuclear half-life of 126 milliseconds. So it doesn't last very long. Basically, if you made a gram of carbon 9, it's going to be gone to the point where you can't even measure it within 10 seconds. Right? So, but all of these are technically possibilities. They're just not going to show up on the periodic table because the only ones that occur naturally are 12, 13, and 14. Naturally on our planet right now. All of these other ones were probably formed, most of these other ones were probably formed at some point during the supernova that led to our solar system forming. But they're not still around because as soon as that supernova was over, then all these really short-lived ones fell apart and disappeared. By the time the humans evolved, by the time life evolved, humans evolved, science developed to the point where we started looking for them, they were all gone. So all of these are isotopes. The other thing that people get tripped up on is when I say, a specific isotope of carbon, they don't think of that most common isotope as being an isotope. Carbon 12 is still an isotope. It's just the most common one. So we assume carbon is usually carbon 12, but it's still an isotope. It's just the one that we default to. And again, those ratios that you find them, so normal proportion, over here is the ratio that you normally find them. 98.84% of carbon on Earth is carbon 12. And then about 1% of it is carbon 13. That's only true on Earth. You go to a different spot in the solar system or a different solar system entirely, those ratios could be totally different, which is kind of cool to think about. They call it if you study planetary science, it's sort of like the astronomy, but not looking at the stars, you're looking at the planets in outer space. Planet scientists refer to that to calling whatever's on Earth normal, they call that Earth chauvinism. Assuming that what's true on Earth is uniform throughout the solar system is not always a good assumption. But since we're here on Earth, we're likely to stay on Earth for the foreseeable future. We will continue to use the periodic table that's focused on Earth. But it is kind of interesting to think about how things could be different to other places in the solar system. All right. Any other questions about counting protons, neutrons, and electrons yet? I'm sure more questions will come up shortly. Let's talk about quantum mechanics, then we'll take a break and we'll talk more about quantum mechanics. This is one of my favorite pictures. I should rephrase. This is one of my favorite pictures that's not of my family. This is a picture from the 1920s from a conference in Europe called the Solvay Conference. One of the reasons this is such a significant picture is in the early 1900s, it was one of the first times in recorded history where you could literally get all of the leading experts on anything worldwide, you could get them all into the same room at the same time. Until the advent of railroad, steamers, and airplanes became widespread, trying to get people from as far apart as Russia and California into the same room to talk about science was basically impossible. So in the 1920s, they started having these conferences where you could get the foremost thinkers on quantum mechanics and experimental physics at the time together. And they would all get into a room and they would present what they'd been doing for the last year. in what they thought the implications were, and then everybody else would argue with them. And so it was basically a lot of good-natured, mostly good-natured, arguing between some really, really brilliant people. And we have transcripts from a lot of these conferences. So we actually have like the tapes of Einstein saying things like, God does not play with dice. Although my favorite response to that, where is he? No, Bohr. Heisenberg's in here too. Niels Bohr was the one who always had the quippy response to Einstein. When Einstein would say something like, God does not play with dice, something that sounds deep and meaningful and is Einstein, so you believe him. Bohr was always the one who would come back with things like, Einstein, quit telling God what to do. So Einstein and Bohr in particular disagreed a lot on the implications of quantum mechanics, despite the fact that Einstein's research led to quantum mechanics. He actually spent most of his life trying to disprove quantum mechanics because he didn't like the philosophical implications. He was a pretty strict determinist in terms of everything must be able to, if you have enough information, you can calculate exactly everything everywhere. And he didn't like the fact that quantum mechanics basically disproved that, which is where Heisenberg comes in. Heisenberg, brilliant guy. I've never seen a picture of him where he doesn't look like a creeper though. He always kind of has like something about his stance and his facial expressions. He always looks like he's like, you're going to turn around and find him right behind you. And historically and personally, not a great guy either. He was the one who was put in charge of the Nazis' version of the Manhattan Project during World War II. So not necessarily someone you want to idolize. I like to make that point not to tear down people, but because you know how they say never meet your heroes? These scientists are just people too. They have their own flaws and beliefs and outdated ways of thinking. So as brilliant as Heisenberg was, he definitely was a flawed person. Bohr was also, wouldn't say flawed. Bohr was probably dyslexic. He was functionally illiterate to the point where he had to dictate his PhD thesis to his mother who typed it for him because he couldn't read. Didn't stop him from becoming somebody that's written about in science textbooks. But it's definitely like these are real people. There's Marie Curie right there. Actually, I think, hang on. Every single one of those boxes is a Nobel Prize. Out of this picture, if we count them all up, there's something like 20 Nobel Prizes out of the 27 people in this picture. And the ones that didn't necessarily earn a Nobel Prize themselves, the dotted boxes mean that their direct student won a Nobel Prize for continuing the work that they started. So this was a really, really big deal. About half of them had won their Nobel Prize already by this point, and the other half were working on the research that would get them a Nobel Prize. And they're almost everybody in here has either an equation, a constant, or a unit named after them. Because of how foundational their research was to basically the entire modern world. Without quantum mechanics, you don't get semiconductors. Without semiconductors, you don't get computers. At least not the way that we have them now. The first computers were not semiconductor based, but for the most part. Marie Curie and Lorentz, late in life, had an on-again, off-again romantic affair as well. After Curie's husband died. I have no idea about Lorentz's personal life, though. He's more of a mathematician. I don't know much about him. Could be. Wouldn't rule it out. They're just people. All right. Then Heisenberg. We're going to talk about Heisenberg today, too. Schrodinger. I pointed to Schrodinger and said Heisenberg. Schrodinger is the one looking dapper with his glasses and his bow tie. Schrodinger really critical to kind of tying all of this together. So now that I've given you a little historical overview, spent some time talking about random people, we'll take a 10-minute break. We'll come back and we'll talk about what they actually did.
LTCC Wi.
Is there a second periodic table still floating around? Perfect. Thanks. One yet?
Yeah. I do it, but not like with the tech. Maybe the other days the milk for that.
The whole thing's fair game, but it's gonna be,
Oh my god.
stuff from row 5 and up and most probably. Yeah, there still will be some from down here. But this is the stuff we care about most. If you know how to use spreadsheets, no. You can do that, or you can come to the beginning of class today. If you wanted to, I'm not sure if you were in here yet. Normally, we can't switch back and forth between lab sections, they're pretty full. But today it would be okay if you have the time and you wanted to, you can come in and touch on that.
When lab starts.
They're all posted online. We have some printed off as well. But so it's your choice.
Okay, perfect, thank you.
No problem.
Question.
Yeah.
Just out of curiosity. Is there like two of them, they're liquid?
Yeah.
Like, okay, right on the app,
Nice.
what is that? Like, room temperature?
Yes.
That's.
It's specifically saying absolute temperature. If you get up to body temperature, then gallium is actually a liquid also.
Oh, okay,
But
okay.
for the most part, we're just talking about at 25 Celsius.
Oh, okay. Is there a reason all of this ones that are radioactive are at the bottom?
Basically, so remember how I was talking about how the neutrons kind of hold things together? When you get bigger than bismuth, then the nucleus actually gets too big for the neutrons to do that. So everything above bismuth is radioactive.
Oh, okay, okay,
And
okay.
it's just because the nucleus gets too big for the
Too big.
neutrons to hold it together.
Oh, okay, okay.
This can't be through. Not working.
Hey, Sean,
Yeah.
what do you think of the Bose-Einstein condensate? Do you think it has any practical uses, or do you think it's ever gonna?
So, The terminology I'm always behind on is, I believe Bose-Einstein condensate is a superconductor, right?
Cause I was reading a little bit on it.
So if we can make there's a lot of research going into what they call warm temperature, high temperature superconductors, because effectively what a superconductor is a wire with zero resistance.
Yeah.
So what that would mean is if you could actually run a wire like that from someplace like Arizona that has tons of sunlight to all the way to San Francisco that has tons of demand for electricity, you could basically cover the state of Arizona in solar panels and ship the electricity across the entire country. Or do something similar with nuclear plants. Basically, it makes it so that you can generate power anywhere and get it wherever you want it to without losing energy along the way. Right now, it's not practical, because wires have resistance.
Yeah.
So if we could make a superconductor that has those qualities, because right now, even the high temperature superconductors are like 77 Kelvin, which is like liquid nitrogen temperatures. So we'd need to liquid nitrogen cool an entire power line from Arizona all the way to San Francisco for that to actually work.
Yeah.
But if we can improve some of that, we can definitely do that. And there's definitely a lot of possibilities when it comes to building computers that have zero resistance within that system, keeping them super cool as a way to eliminate resistance and actually get better numbers from it. So I believe most quantum computers are super cooled as well. So there might be some applications in situations like that too. It's definitely, they call that exotic states of matter, just because they don't happen naturally on Earth. But there's definitely some use to it out there. It's just a matter of, can we make it feasible?
Yeah.
Metallic hydrogen, another one. I believe that that's a Bose-Einstein condensate that they believe they found evidence for in the core of Jupiter. That is, I believe that that's a superconductor as well, so it should be a Bose-Einstein condensate as well. But it turns out there's actually a lot of different phases of things. We kind of simplify it to solid, liquid, gas, but there's a lot of different versions that have different properties like that.
Was it in one of these conferences where Schrodinger came up with a Schrodinger's cat?
It probably was this, I believe that he had put it into writing before they got to this conference, but basically the whole point of Schrodinger's cat was trying to illustrate that you can't apply quantum ideas to the macroscopic world because it doesn't make sense. Then it's the opposite way now, like, hey, in the macroscopic world, this is what it would look like, and that's weird, but that's actually how it behaves. But yeah, and the
So he was more aligned with like Einstein's kind of thing.
no, he was basically saying that you can't. So Einstein didn't believe the probability idea of quantum mechanics. He didn't believe that there was that the Heisenberg uncertainty principle was real. He thought there must be some hidden variable we couldn't see, which still might be true, but it's not science if we can't test it. So it was basically Einstein disagreeing on philosophical grounds, whereas Schrodinger was more talking about like, hey, all this really weird math, all this really weird stuff is happening, only happens in these very specific situations.
We would struggle, I was like, I'm guessing, it was like, yeah.
And I believe there's actually been a fair bit of research. I'm trying to think of what the specific term is that they use, but there's been some research. There's a specific mathematical and physics theorem that effectively shows, if its assumptions are correct, it shows that there are no hidden forces. That Einstein was just straight up wrong about that. But it's very, very abstract, and I can't even remember the name of it off the top of my head. But basically, all of the stuff that Einstein didn't like about quantum mechanics has mostly been supported by everything in the last 100 years.
How do they calculate half-life?
So things that have nuclear decay follow what we call first order kinetics, which basically means exponential decay.
Okay,
So if you start with a certain amount of carbon-14. You plot the amount of carbon-14 versus time. It's gonna take a certain amount of time to get to half of what you had. And then if you give it the same amount of time again. It doesn't go to zero, it goes to half of the half.
okay.
And so they call it, it's for nuclear reactions, and it turns out there's a whole class of reactions that fit this model. But so for those type of reactions, you can model, the half-life is gonna be constant. The half-life of carbon-14 is 5,730 years, I think. Every 5,730 years, you have half as much carbon-14 as you started with.
Okay.
And every isotope has its own unique half-life. And you don't need to be around for 5,000 years to measure that, because if you know it's exponential decay, you can basically take 2 data points way up here. And you can calculate the form of the entire function.
And does stable just mean that it's not really feasible to?
Stable means it doesn't do this on the time scale, basically the time scale of the universe. So there are a lot of unstable, there are stable isotopes in that we will never be able to observe them decaying, but they could be more stable. If we took them apart and rearranged them, they could get better. But we're not gonna see them decay like we do with some of these others.
Makes sense, thank you.
All right, I know we still have people coming back in, but we're about 10 minutes in, so let's talk about quantum mechanics. So Niels Bohr, one of my favorites, probably my single favorite person out of that picture. One of his famous quotes is, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." In other words, if it makes sense to you, you're not thinking about it right. That's normal. This is gonna be really weird. Because everything about our brains and the way we process the world around us is evolved to deal with the macroscopic world, things that operate on our scale. We literally don't have senses, and the way that our brains are wired cannot really truly understand quantum mechanics. We can use math to approximate it, we can use analogies, but they all kind of fall apart eventually. So part of this is just gonna be, yeah, it's weird. But that's kind of all of our best understanding says that it's true. Alright, so. One of the things that first led to this was an Italian scientist named de Broglie. Realized that they were basically what started the whole quantum mechanics debate about whether it exists at all. Whatever started this entire field was basically this idea that they couldn't decide whether light was a particle or whether it was a wave. What Einstein actually won his Nobel Prize was not actually E equals mc squared. He actually won it for his work on work function, which is basically proving that light occurs in discrete packets. So is it a wave or is it a particle? Well, Einstein's research suggested it's a particle, but they also could do all this other research and say that it was a wave. So what de Broglie did was he realized that, well, it's not just light that behaves this way. Any matter, when you get it small enough, behaves like it's both a particle and a wave. They call this wave-particle duality. Everything is both a wave and a particle. Part of that comes back to Heisenberg uncertainty principle. Heisenberg's uncertainty principle is a mouthful, but it's a way of basically saying that your uncertainty in a particle's position, which we represent with this Greek letter sigma, and x just means position, where it is. So our uncertainty in a particle's position times the uncertainty in a particle's momentum is always greater than or equal to a constant. This constant is just a number. It's a weird number. It's called Planck's constant. Remember how I said everybody on that last page either had a constant or an equation named after them? H is Planck's constant. And the Heisenberg uncertainty principle just says that you can't know with absolute certainty both where something is and how fast it's moving. You know one, you can't know the other. And if you look at these are multiplied together. So the more accurately you know particle's position, the greater the uncertainty in its momentum. So one of the analogies I like to use to think about this is if we hung a basketball from the ceiling right here, and this room was pitch black, and I'm standing over there by the whiteboard, and I'm trying to find where that basketball is. And I'm going to do that by throwing baseballs at it. I can throw baseballs around this entire room, and just by the sound, I can tell when I hit the basketball, right? But as soon as I hit the basketball with a baseball, what happens to the basketball? It starts moving. I now know really certainly where it was a second ago, but now it's moving. I decreased the uncertainty in its position, and I increased the uncertainty in its momentum. And it turns out that's what happens at the atomic scale when you get to the things the size of electrons, because the only way we have of measuring where electrons are is by shining light on it. But light has momentum, like throwing baseballs at something. So the second you measure where an electron is by shining light on it, now it's somewhere else. So you know where it was, but not where it is and its momentum. If you measure its momentum, we measure its momentum by letting it bounce off of something and measure how it bounces off. Well, as soon as it bounces off of something, it heads off in a different direction. So if we know its momentum, now we don't know where it is anymore. Yeah.
So that isn't to say that it doesn't have both a position and
Right.
and so it's just that the act of measuring it changes it. So.
The act of measuring it changes it. And it turns out when you get to small enough things, this wave particle duality actually kind of takes over, and we treat electrons like they're in a bunch of places at once. And that's a little bit like a guitar string. If you know you can know where a guitar string is. That's a quarter, that'll do. Thought I had a pick in my pocket. You can know where a guitar string is, but as soon as I give it some energy, it starts vibrating, right? So we can treat guitar string like it's vibrating, and we know that the string is fixed at the two ends. But as long as it's vibrating, it's moving back and forth. We don't know exactly where it is between these two extremes. And what's more is we can't just have any wavelength we want. So okay, sound is a wave. Guitar string vibrating is like a wave. That's not necessarily new idea. But it turns out we can only give that wave certain energies. In order for us to make a standing wave, the positions at each end have to be fixed. In other words, if you try to play a guitar where one end of the string was free to flop around, it's not a very effective guitar, right? You can't make a standing wave on a string unless you fix both ends of it. Which means that there's only certain energies, certain frequencies that you can make with a guitar string unless you change how big this box is. So without changing how big the box is, I could just strike the string open. I can put a node right in the middle where there's no vibration. I'm just putting my finger right on the string, exactly halfway between the two ends. Once I do that, I make a wave that sounds like this instead. I can't do that just at any point along the way because I need to be able to make a wave where both ends are still secured. There's a few different times you can do this. Does anybody play a stringed instrument in here? Does anybody know what this is called? Harmonic. A harmonic is basically when you can create a standing wave of different frequencies without, you're changing the wavelength, without changing the size of the box, basically. If I just push down right there, that changes the frequency too, right? That's all changing, but what I'm doing there is I'm changing how big the box is. I'm still fixing both ends of the guitar string. Without changing the size of the box, I can still change the pitch. By just letting it, putting a node, one spot where it doesn't vibrate right in the middle. There's only certain frequencies will let you do that. It turns out that's how electrons behave too. Electrons behave like a wave in that they have, that we know that they're somewhere in this box. Where they are exactly in this box, we can't say. Just like we can't say where the string is at any given second. It's vibrating, it's in all those places simultaneously. But we can change the energy level of the electrons by changing this function, by changing the wavelength. So this is some of the first evidence that they had in favor of this wave-particle duality, is that they could show that electrons move between energy levels and that they can't exist in between. If I try to play a harmonic, I can play a harmonic halfway, I can play a third of the way, I can play it maybe my quarter again. So halfway, a third, or a quarter. But I can't play it in between there. If I try to just play it at random, just under halfway, it doesn't do anything. If I shift my finger just a little bit so it's exactly halfway, I get a harmonic. Electrons cannot exist in between energy levels. Just like I can't put a harmonic just anywhere on the guitar string, I'm limited to only positions, only frequencies that have these specific wavelengths. Electrons cannot exist in between different energy levels because they behave like a wave, because they're so small that this uncertainty is really, really small. So as long as your object is large enough that you can see it, or even if it's just the size of the mass of a nucleus, basically this uncertainty is much smaller than the actual mass. But because things like electrons and photons and other fundamental particles have masses that are either non-existent or so small that this starts becoming important, they only really can exist at certain frequencies. Right, so another way you can think of this, if you think about taking this guitar string, instead of putting it in a straight line and fixing the two ends, you can picture taking those two ends and fixing it in a circle. So now we've got a circular guitar string. We'd still have to find some way to create tension. So the guitar string analogy starts to fall down a little bit. But it's basically, it's a wave, just like a guitar string, except it's circular. Well, it's not really circular because atoms aren't two-dimensional. Atoms exist in three-dimensional space. So really, it's more like it's a sphere. We have this wave where we can find an electron that looks kind of like a sphere that surrounds the nucleus. And that specific shape is what we're referring to when we talk about an energy level. We're saying an energy level is how close is that electron to the nucleus. The further apart we get, further we lift the electron away from the nucleus, the higher that energy system is. Right? So similar to picking, another good analogy is books on a shelf. You can put a book on shelf number 1. And that's gonna be your most stable shelf. That's gonna be your lowest energy shelf because it's closest to the ground. Or you could take a book off of shelf number 1, you could put it in shelf number 2. Can you put a book in shelf 1.5? No, there isn't a stable state between 1 and 2 for you to put a book. Again, like the analogy falls apart if you dissect it too much. But what I'm really getting at is that there is nothing between these where you can put a book, where you can have a stable state for these electrons. And the further up you get, the further away from the nucleus you get, the higher the energy is. You can picture taking a flimsy IKEA bookshelf and filling it with every textbook that you've ever had to buy, high school and college, and putting all of them on the highest shelf. Is that a very stable system? What happens the first time we get an even smallest little earthquake? The whole thing's gonna fall down, right? The higher up you get, the higher the energy system, the less stable it is. All right, and so we can move electrons between these energy levels. So this is a version of what's called the Bohr model. Niels Bohr was the first one who came up with this idea that, oh, okay, we're only seeing certain frequencies of light from these systems. It must be because the electrons can only exist at certain energy levels. So Niels Bohr was one who came up with this idea that these different energy levels, these different shelves that you can put the electrons on, we can move the electrons between those levels, but we have to put in energy to do it. And when you put energy into a system, how do we find some way that we can actually put energy into something as small as an electron? We shine light on it. Light's about the smallest thing that exists. So if we're trying to manipulate something that's really, really small, a lot of times we use light to do that. So in this case, if you shine the right frequency of light on an electron that's in one of these low energy levels, one of these low shelves, by shining light on it, you can get it to jump up to the next energy level. They call that promoting an electron. When you promote an electron, now it's unstable. It was stable down when it was at the lowest energy state, now it's at a higher energy state. And so it'll naturally relax and fall back down to the lower energy state. I don't know if any of you have ever had a job where you liked your job, but then you got promoted to being a manager. It's a higher stress environment, right? You get a promotion, all of a sudden it's higher energy, it's less stable. And it's really, really relaxing when you get to go back down to just being a server or something, right? At least it was for me. I don't like being a manager. Some people like the opposite, but that doesn't work for our analogy. You get a promotion, it's higher stress, higher energy. You relax when you fall back down to lower energy. The difference in energy between these two energy levels dictates the frequency of light that you have to use to promote it. And it also changes the frequency of light that is given off when it relaxes. So the way that this works, it's weird. When you promote an electron using light, you shine light on an electron, it bumps up to a higher energy level, the light disappears. The photon is gone as soon as you do that. But don't worry, we can get it back. Because as soon as it relaxes, it gives off energy in the form of light. So basically, we think of photons as being a particle, something that exists definitively. Turns out, a photon is just a way of moving energy around. If you move energy into this electron, it bumps up to a different energy level. So what happened to that energy? Now it's stored in this higher energy electron. When that electron falls back down, when it relaxes, you give away the energy again. You create a photon again. Which is a little weird.
Is it the same energy level coming out that was put in?
Yes. If you're really careful about this, if you shine light on this that's greater than this difference, basically what can happen is sometimes there's more than one possible state up here. If you shine a light on it that bumps it all the way up to this highest level, if they're close enough, it can fall back down to here until it reaches a gap. And then when it reaches a certain gap, when it falls down, it gives off light. But we can change what that gap looks like by changing these energy levels, by changing what elements we're talking about. Different elements, different nuclei are going to have different energy levels. Because what's different about different elements? Number of protons. What do protons do to electrons? They attract them, right? So the more protons you have in the nucleus, the more you're going to pull these electrons in. It has the same effect as tightening a guitar string. I can tighten the guitar string and that mimics pulling these electrons in tighter. They're pulled in tighter, they're less able to flop around on their own. So by changing the element, we change what these energy levels are, which means we change the type of light that we get from these systems. So every element has its own set of orbitals, has its own set of energy levels. When you change those different energy levels, or when you shine light on it, or you excite it in different ways, you can excite it just by heating things up, by passing a current through it. When they fall back down and they generate all of these different wavelengths of light, each one of these wavelengths of light corresponds to a different jump between energy levels, a different set of shelves that you're moving between. And every element has its own unique spectrum like this. So it turns out nothing actually looks like the Pink Floyd shirt with the white light goes through a prism and you get a rainbow. That only happens if you've got a mixture of a ton of different things creating that light. Like our sun's got a whole bunch of different elements inside it glowing because it's so hot. But if mixing all of them together, you get something that looks like a rainbow. But if you take any pure substance, you get something that looks more like a barcode. A barcode that's kind of rainbowy. So this is barium. Barium has a bunch of different transitions that can happen that all happen to fall in the visible region. Where the wavelength, the frequency of those transitions matches things that we can see with our eyes. A lot of elements don't have transitions that we can see visually. Our eyes evolved to be able to see photons that come from the sun because we live on Earth and our sun is the sun that exists when life was first developing. If we went to a different solar system, or if life evolved in a different solar system, their visible range would be very, very different, even if they even had eyes. But let's assume that they had eyes. Their visible range would be different than ours because it would match their solar spectrum, not ours. But looking at these different barcodes, this is how we can tell without ever actually getting a sample from, say, Jupiter. We know what Jupiter is made of. Because we can look at the light that bounces off of Jupiter and we can look at it and treat it like it's a barcode and say, oh, Jupiter is mostly hydrogen with a little bit of helium. We can tell that just from the wavelength of light that comes off. Because every type of element is going to have its own distinct barcode. All right, so another word for these energy levels, and we're going to get a little bit more specific with them because it turns out there's different types of energy levels. The word we use for them is orbitals, and this comes back from Niels Bohr once again. Came up with this idea. Originally, they still didn't really understand how electrons behave. They thought, oh, they're just moving so fast that we can't pinpoint where they are. So we're just going to say that they're orbiting the nucleus. Right, so that's where you get that classic atomic symbol that looks like this. Is that better, if you're better at art than I am? That looks familiar, right? They came up with this idea because they thought these electrons were actually traveling in a path like a satellite around Earth. So they called these, the different energy levels where you can find these electrons, they called them orbitals. Because it's kind of like they're orbiting the nucleus. Turns out they don't actually orbit like a satellite. But it's still, that language is carried over. All right, so these different orbitals, turns out different shapes, different energy levels can hold different amounts of electrons. If I go back to that picture of the bookshelf, not each one of these, the way it's drawn here, it's kind of hard to tell, but basically different energy levels kind of get wider as you get up there, so you can fit more books on them. The higher energy levels you can put more electrons into. So it's not really like this. If you can picture a bookshelf that is like an upside down triangle, almost. Where as you go up, every level you go up, you can hold more electrons in it. Not something we would see what I mean about how analogies all fall apart when we dissect them far enough. So the different, at its most basic, the lowest energy level can only hold 2 electrons. As soon as you get more than 2 electrons around an atom, you have to go to the second energy level, which we call n equals 2. So n is what's called a quantum number. I'm not going to test you on the quantum numbers, other than to say that n equals 1 just means the lowest energy level. N equals 2 is the second energy level. As you keep going up, you can fit more and more electrons in. Well, this sounds, I told you earlier today that I wasn't going to make you memorize something for the sake of memorizing, right? I'm not going to make you memorize this. Because you have a periodic table. Remember Mendeleev? Remember how he put everything into the periodic table and he put everything that had similar properties in the same columns? He didn't know it because this was the 1800s, but what he was doing is he was organizing the table around how many electrons were in the highest occupied energy level. So what we're actually looking at, if you look, I just said that the first energy level can hold 2 electrons, and then you have to go to the second energy level. Look at your periodic table. How many elements are in the first row? 2. Because as soon as you get more than 2 electrons into a system, you have to go to the second energy level, which is the second row of the periodic table. So basically the shape of the periodic table is not chosen at random. The shape of the periodic table is chosen because it's representing how many electrons can you fit into each of these different energy levels. So it turns out we can actually further divide this. This is the simplified way of doing things. I don't think this explains much, and it just feels like it's actually still kind of memorizing things. Why do we have these 2 columns all the way on the far left and then a big gap, and then we have more columns over here? It turns out within these individual energy levels, there's a suborbitals. We can basically split it up further. And the different types of orbitals we just use letters to describe them. So the simplest type of orbital that you can have is an s orbital. It just is shaped like a sphere. However, once you get to the second energy level, you can still have an s orbital in the second energy level. But then there's also this shape called a p orbital. And that's kind of like adding that harmonic. If you think of the different energy levels as the different strings on the guitar, you can change what frequency you're playing in based on what string you're using, right? Within the same string, you can add those harmonics, and that corresponds to the different shapes of the energy levels of these orbitals. So if an s orbital just looks like a sphere, a p orbital kind of looks like 3 figure eights on top of each other. Or even better, if you can picture holding 6 balloons all by the knot at the same time, you're going to get this sort of weird 6-sided object. It's going to kind of look like like 3 figure eights laid on top of each other. One that goes up and down, one that goes left and right, one that goes in and out. Basically, they're aligned to be 90 degrees from each other. So if you've taken an algebra class where you had to do a 3D graph of anything, think about your X, Y, Z axes. E was always up and down, right? And then it was X, Y. Picture drawing a figure 8 along each of these axes. And that's kind of the shape you get from a full p orbital. P orbital can fit a total of 6 electrons in it because you can put a pair of electrons into each of these figure 8s. So go back to your periodic table. What does it say underneath those first 2 columns? Very bottom says S block, right? And it's 2 elements across because an s orbital can only hold 2 electrons. If you jump across from, say you go from beryllium number 4 to boron number 5, that next section there is 6 elements across. It's 6 elements across because that's the p block. That corresponds to, if you're adding electrons into a p orbital, it's like counting across in the p block. And so every time we go up an energy level, we add a new type of orbital. So when we go from 1 to 2, we added a p orbital. When we go from 2 to 3, we add another type of orbital. What do you think that orbital is called? D orbital, yeah. So this middle section here is called the d block. It's 10 elements across. So how many orbitals or how many electrons do you think you can put into a d orbital? 10. So another way of drawing this, it kind of goes back to the bookshelf analogy. We're going to make the y-axis here energy. We're basically going to start the lowest possible state that you can have. The lowest possible energy that an electron can have is when it's in the first energy level in an s orbital. And that can hold 2 electrons, which is why there's 2 elements in the first row of the periodic table, hydrogen and helium, right? So hydrogen corresponds with having 1 electron in that 1s orbital. We use arrows to differentiate these because it turns out they can be, they're not physically pointed in opposite directions, but it turns out that if you change a number sign, if you change a negative sign in the function that describes this, you can actually, what allows it to hold 2 electrons is if you have basically a positive version and a negative version. Not in terms of charge, but in charge of basically the function has an extra negative in it. So they call that spin. I'm not a huge fan of that term because it implies the electrons are spinning around the nucleus or orbiting one way versus the other way. They don't physically spin, but mathematically it looks a lot like the fact that if I took a basketball and spun it on my finger, I could spin it clockwise or I could spin it counterclockwise, assuming I was coordinated enough to do that. I could give the same basketball the same amount of rotational energy in 2 different directions. And that's kind of what spin is for electrons. It's not physically spinning, but basically they can be offset from each other and fit into the same space. Once we fill up that 1s orbital, though, we've reached the end of our first row of the periodic table. So if we want to add a third electron, it has to go into the second energy level. Whoa. Went too fast. So here's our 1s. Once we fill up the 1s orbital, if we want to add more electrons, we go to the 2s. How do we know that? Because we look at our periodic table. Once you're done with the first row of the periodic table, if you're counting along with the atomic numbers, you get to number 3. Number 3 is in the second row, which tells us this is the second energy level. And it's in the s block, which tells us we're putting the electron into the 2s orbital. That would correspond to lithium, 3 electrons. They're always going to go, the most stable state is going to be in the 1s. Once you fill up the 1s orbital, you go to the 2s. Once you fill up the 2s, we need to find somewhere else to go. So follow along on your periodic table, we jump across the boron, which is still the second row, but now it's in the p block. So as we keep adding electrons, now we're going to stick them into the 2p orbital. So we count from left to right. So boron, carbon, nitrogen, oxygen, fluorine, neon. We added 10 electrons. And now we've filled up the 2p. We've finished the second row of the periodic table. So what's going to happen next? We're going to go to, I'm going to skip yellow. We're going to go to not the D yet. We've got to go to still back to the S block because we're after 10 comes 11, right? So look at sodium, third row, and it's S. So the 3s orbital is going to be where we put the 11th and 12th electrons. What do you get after magnesium? Where are we going? Silicon? No, not yet. Aluminum first. Then silicon. You're right there. So we still jump across this whole D block to get to 13, which is aluminum, in the P block. So 1, 2, 3. There's our 3p. As we get to larger and larger systems with more and more electrons, we're just going to keep doing this process. What do we get after argon? This is argon right here. There's a total of 18 electrons there. I know it's argon without even counting the electrons because I can look at the periodic table. What's at the end of the third row is argon. Argon has 18 electrons and it corresponds to filling up that 3p. Where do we go after that? Potassium. Which block is that in? 4s. Now we get to the D block. The D block is where things start getting a little tricky. There's just one rule you need to remember. And that's that, remember when I said every time you go up an energy level, you add a new type of orbital? So even though the first D orbital shows up in the fourth row of the periodic table, it actually belongs to the third energy level. Just like if I play a high enough harmonic on the guitar, I can make a string sound higher in pitch than the one that's underneath it. Right, so I can get to a higher energy state without changing the string. Go back to the other color green. So our first d orbital belongs to the third energy level, but it comes after 4s. 3d is higher in energy than 4s is. So even though the first d orbital is part of the third energy level, we're actually going to start filling up 4 before we finish filling up 3. So basically what you need to remember in terms of reading your periodic table is your D block is offset by a row. So even though the first row of the D block is in the fourth row of the periodic table, it corresponds to the third energy level. Why does this matter? Well, because it turns out describing where these electrons are and how many electrons you have is going to dictate a ton of the properties of these different materials. All those different orbital energies and how close they are to each other, they dictate things like what color light it absorbs or emits, which is cool. It doesn't sound all that terribly useful, but they also dictate things like how stable it is in its metallic state. Some metals rust easier than others, right? We can describe that and we can predict that by looking at where their electrons are, what their electron configuration is. So this drawing, would be a atomic orbital diagram. I'm not going to ask you to recreate this. I can do this from memory because I've done this enough times, and this was what I studied in grad school. All you have to be able to do is follow the periodic table, and we're going to use a shorthand instead of drawing this every time. Instead of drawing it out every time, if I wanted to write the electron configuration here, we just use a shorthand. Because these orbitals always go in the same order, mostly, if I'm going to write the electron configuration, I can just say 1s, and I'm going to say it has 2 electrons in it. And then I'm going to say 2s. How many electrons are in 2s orbital right now? Just the s part of it. The total number of electrons in n equals 2 is 8, though, because you get that. So 1s2, 2s2, 2p6. After 2p6, what happens? 3s. And how many electrons does it have in it? 2. And 3p6. And what happens after 3p6? 4s2. So what element has this electron configuration in its ground state? When it's neutral, only one element is going to have this many electrons and have this specific electron configuration. Calcium. The last electrons we put in here were in the 4th row in the S block, and there were 2 of them. So you go here, your periodic table, go to the 4th row, S block, count 2 spots over in the S block. Calcium has this electron configuration. And it behaves the way it does, it reacts the way it does because of its electrons. All right, so how many electrons can we fit into a d orbital? 10. What element is that? You don't have to count them all the way from the beginning. We just finished 4s, and then I went ahead and filled up 3d. Zinc. So when we're writing these electron configurations, all you have to do is follow the periodic table. You know how to use your periodic table, it's not memorizing. You look at the shape of the periodic table and that tells you everything you need to know. The trickiest part about it is that d orbital is offset by a rho. You about to ask a question?
So what would be using that?
Let's talk about the F block. So every time we go up in energy level, we add a new type of orbital, right? So when we went from 1 to 2, we added a p orbital. We went from 2 to 3, we added a d orbital. When we go from 3 to 4, we add an f orbital. The f orbital is these bottom 2 rows, or sorry, the f block are these bottom 2 rows. But they don't show up until after 56, after barium, right? So they don't show up until the 6th row. But they technically belong to the 4th energy level. So just like the d orbital, the d block is offset by 1 row, the f block is offset by 2 rows. For a similar reason. Basically, there's a lot of other stuff you can fill in that's more stable before you get to that 4f. Right, so if we wanted to do something like, let's look at lead. Lead, number 82, Pb. If we want to write the electron configuration for lead, I'm not going to draw this out because now I've already filled up the whiteboard space I have and we just only made it to zinc. We need twice as many electrons to get to lead, more than that. So I'm just going to use the shorthand for it. And I'm going to follow along the periodic table. To get to lead, I'm not going to do the color coding this time because it's going to take forever. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. After 3d10, what do we do? Well, keep counting. End of 3d10 was zinc, right? So gallium, we're back to following our normal rules. Gallium is in the 4th energy level, E block. And we're going to fill that up. We're trying to get all the way to lead. So 4p6. That corresponds with getting to krypton, right? So once we start getting these really long, this order never changes. If we're going past this, it's the same order every time. So if we're trying to go past this, we can actually use a shorthand. Just put a noble gas, something from column 18 in brackets like this. That means everything is the same up to krypton. And then we keep going. So after krypton, after 4p6, we're in the 5th row now. In the s block, hold 2 electrons. And then what? Yeah, 5s2, and then 4d10, because we're going all the way through it. Then we're back to the p block, right? 5p6. That matches up with xenon now, right? Now we're almost there. So if I told you to write out the complete electron configuration, you would write all of this. You would skip the krypton and you would just keep going. Basically, writing the krypton in brackets is a way to not have to rewrite this every time. If I wanted to start, usually what you want to do is start from the closest noble gas before the element you care about. So xenon is the last noble gas before we get to the row that has lead. or our fastest version of this would just be xenon in brackets. 6s2. Now what do we do? After 6s2, that's 56, that's barium, right? Where is 57? It's in the F block. So this shape, the way that this periodic table is designed is so that it prints well on a piece of letter paper. It actually, the F block actually goes in between barium and lutetium. So it would be stretched out like this though, which doesn't print well. So basically this black line, this is basically saying this is an inset. This goes between columns 2 and 3. So it goes 6s2, then we get to the F block. And the first F orbital is part of the 4th energy level. The first F orbital is part of the 4th energy level. Just make sure I said that correctly. Ever say the same word so many times they stop making sense? So it's 4th energy level. It's an F orbital. How many electrons can an F orbital fit? 14. Close. If you're looking for the rhyme between the reasoning for why it goes 2, 6, 10, 14, it's 2 times odd integers. 2 times 1 for an s orbital, 2 times 3 for a p orbital, 2 times 5 for a d orbital, 2 times 7 for an f orbital. If there was a g orbital on here, it would hold 2 times 9. It would hold 18 electrons. We've never discovered an element that has a g orbital, but we know mathematically they exist. So, but they don't show up on your periodic table, so they won't show up in any electron configurations we need to worry about. All right, after 4f14, that gets us to ytterbium. Number 70. We're almost to lead. After 4f14, what do we do? 5d10. This is as complicated as any of these will get. What happens after 5d10? 6p2. Bingo. There's our electron configuration for lead. A lot of numbers and letters up on the board. But all we did was follow our periodic table with those 2 exceptions. D blocks offset by 1, F blocks offset by 2. And we just counted until we got to 82. Okay, last thing, and then we'll be done. Lead's not really very stable as a metal. Lead is actually much more stable when it's an ion with either a +2 charge or a +4 charge. What would the electron configuration for lead look like if it was a +2? If it's a +2, we have 2 less electrons, 2 fewer electrons. This is what it started as. If it's an ion, you always write what it starts as, and then we're just going to basically cross stuff off, or we're going to add some extra electrons if it has a negative charge. If lead is a +2, we're just going to get rid of those highest energy electrons, 2 of them. So if it was a +2, it would be xenon, 6s2, 4f14, 5d10, full stop. What about if it's a +4? We're going to be taking away 4 electrons. Where do we take them from?
5.
Seems like we filled up 5D, the last one before 6P, right? The thing is, once you fill an orbital, it gets super stable. And the larger the orbital, the more stable it gets once it's full. So basically, once you fill a d orbital, you're never going to break it up. So we take it from the 6s. There's only 2 in there. That's the smallest possible electron you can have. So what this brings up is the idea of what are called valence electrons. Valence electrons are the electrons that are in the highest occupied energy level. So for lead, our valence electrons are in the 6th energy level when it's neutral. And it has 4 of them. Lead has, when it's neutral, has a total of 82 electrons, but only 4 of them are in the valence energy level. It only has 4 valence electrons. And the valence electrons are the ones that you'll actually move around. You basically will never move what we call core electrons. Core electrons are everything below the valence level. So when you take electrons away, they always come from the valence level, never from a full d orbital or full f orbital. All right, good job hanging in there. I know that was a weird one. I'll see half of you in lab. Everybody else, check the quiz tomorrow. We'll do practice for this on the quiz. Good. This is my favorite part of chemistry too.
I know, because it's right all that. Oh, yeah, that makes so much more sense. Yeah, that makes sense. Yeah. I was like, oh my god. Now, yeah, that makes perfect sense. I was like, probably. Yeah, so that's. Yeah, and then you just saw that. Huh.